Thank you everyone for coming. Slight change in the title. Uh, who says you can't use Gradle to build a monorepo? But rest assured, you're in the right room. I am Ashwin. I am a member of the Kotlin platform team at Doordash.
I'm Yunji, same team with Asher.
Before anybody said anything, I'm just gonna address the elephant in the room. It's probably on everybody's minds right now. Yes, we looked into Bazel, but we're not at BazelCon now, are we? So we're going to talk more about Gradle today. So I want to start out with an intro of backend development at Doordash. I'm going to talk about the problems we were facing, how we explored Bazel, how we went back to Gradle, and how we sort of got it to work for our use case. We're primarily a Kotlin shop. We write Kotlin microservices for the backend. We have over tens of millions of lines of Kotlin code, and we have about 700 backend developers, and this code is split across about 200 repositories. If you want to read more about why we picked Kotlin, scan that QR code. I'll leave it up there for a few seconds. But essentially the problems that we were facing were that like build pipelines and IDEs used to degrade very quickly as you get to a large repository. Since we had a lot of separate code bases, developers tended to create utilities, build pipelines, and build codes that were performing essentially the same function, but they differed when they didn't need to. Everybody knows about the log4j stuff, so upgrading dependencies becomes a really complex endeavor involving multiple organizations and people. Is something that, we would have preferred to avoid. And propagating best practices in tooling and, making sure that everything is defragmented is a never-ending task. There's almost always someone who's going to be on like older tooling. Hang on. This one. Okay, so basically, what we concluded was building a monorepo would help. It does come with a lot of challenges to the build system and other things, but this talk is focused more on build systems. So skipping back to the right slide. So we start out with exploring Bazel. Well, you know about the pros. It's designed for large monorepos. You get distributed builds and remote execution right off the bat, and you have the opportunity to unify build systems across your whole stack. It also came with a lot of cons. In our case, all of engineering would need to migrate to Bazel. They would have to encounter that learning curve. So not only like migrate their build code, but also learn Bazel, which will slow them down. We know that the Kotlin development experience on Bazel is subpar, and there are a lot of specific plugins that are available in Gradle that are just not there in Bazel. I mean, we could bring them, we could try to recreate it, but it would take a lot of work. In addition, we also had several custom plugins that we developed to improve developer experience. They help reduce build boilerplate. They optimize Maven repository settings so you aren't like downloading too much stuff. They apply our internal code quality rules and just like standard application settings. Again, like replicating this in Bazel would take work. And lastly, Kotlin is almost married to Gradle. You can separate them, but it's going to be hard. And at the end of the day, our company is a rocket ship, like many companies are. Developers can't pause all development to migrate build systems. So we had to think about ways to upgrade the rocket mid-flight. Cool. So we're back to the drawing board, and we're thinking about, is Gradle still viable? First of all, I want to talk a little bit about, just to give a brief intro of like different kinds of Gradle project structures. Starting out with, a single project build, which is the most common by far. You'll have a build file, a settings file, and, your source code. The next logical progression after that is the multi-project Gradle project, where you have distinct sub-projects within that project, but there's a parent Gradle project that everybody's kind of linked to. So each of the sub-projects have their own build file and source code, but there's also a root build file and settings file. this, it helps you scale a bit more, but after a certain number of subprojects, you do run into degraded build latency and IDE latency because you're indexing everything, you're almost building everything. You can cache some of the stuff, but you're building a lot, and especially because everything is linked together, it's hard to separate them. And that brings me to the last project structure here, which is the composite build. And this is what we're going to be talking a lot more about during this presentation, which is the composite build. And you have the concept of different projects, which are sort of loosely independent. They have their own build files, setting files. They don't have a parent project that they're linked to. And they could have interdependencies among each other, but they can be built independently or together, whatever works best for your use case. So let's talk about the pros and cons of composite builds. So the big pro was that we already had a lot of in-house expertise with Gradle. Staying with Gradle lets us keep the third-party plugin ecosystem and custom internal plugins that we already have. And you have a significantly better developer experience with Kotlin and Java. And same applies with the IDE experience. The cons are, you don't have distributed execution. It's available just for tests with Gradle Enterprise. Remote execution is not supported, and there's no exposure of the project graph within a composite build or an aggregation of composite builds. And it doesn't solve our problems with the rest of the stack. So, web, iOS, Android, still a problem. But we decided to go forward with it because we wanted to use the best build tool for the job for each platform. So obviously we had to make some augmentations when it comes to composite builds, and I'll let Yunji talk about those.
Thank you, Ashwin. So Ashwin just mentioned some cons in the composite builder, and I will just share you how we overcome those cons and make a Gradle composite builder a very suitable build system for the Monorepo. But before we dig into the details, let's look at a more general questions. How do you do tasks correctly, faster, and efficiently? I think this is most what the DPE is focused about, right? When I'm thinking about these questions, it keep reminds me how similar we do things when we at school and versus we do things when we in industry. So first, ask yourself, how do you do things correctly in school? I will give you an idea. To make sure everything is correct, you directly copy the answers from the cheat sheet instead of thinking out yourself. And in industry, we have a fancy name for cheat sheet. We call it a single source of truth. Basically, this is a file to log all the ultimate data values and such as dependency variance. And then, how do you do your work fast? I think at school, you could do as little work as possible and tell your teacher all done. That's pretty smart, right? And in industry, we call this as a minimum set of change targets, which means we only build and test which is changed and leave the other parts untouched. The last question, how do you do your homework efficiently at school? I think the most efficient way is just ask your classmates to do your homework for you. And in industry, we call this distributed execution. I just love the terms we use in industry. And as you can see, the behind the principle is quite similar, but comes with different consequences. If you follow the previous actions in school, your teacher will tell you, stay after school, you get detention. But if you do it in industry, your manager may come to you say, hey, congratulations, you got your promotion. Next, I will just share you the exact secret behind how we did things correctly, faster, and efficiently in Doordash. And after that, please send me a message if you get your promotion. All right. So this is how we did it. We have a couple of design principles. The first is to make sure the correctness. And here I want to mention about the dependency variance specifically. So please raise up your hands if you have ever encountered issues caused by mismatched dependency variance. Exactly. A lot of you heard, I'm sure you heard about no such method exception, class not find exception. And for those who did not raise your hand, you should do more coding. And because this is a dependency mismatch issue is very common, and it is also quite hard to find it because it will not show up until it's hit into the runtime. And the next is to build fast, right? So to do it faster, we only build what is changed, and we do not do the full build ever. The last is efficient. So to do that, we distributed the build into different machines. No, I'm not asking my classmates or colleagues to do that for me. We build in-house build services to do this distributed building work. And the last, definitely, the most important principle is the emphasis for developers. And this is exactly why we gathered today at this DP meetings to seek great ideas how to improve our productivity. All right, so let's see each one in details. What you see here is a classical composite builder, Monorepo structures. So in our repository, there are a bunch of projects that sit together, and we categorize them into libraries and services. For the libraries, basically, they are a bunch of shared code by different projects. And for the services, it has a main method as an entry point that could be deployed to the production environment. So in this case, each project has its internal dependencies. And for the dependencies, we also make it into two types. One is called in-project dependency. Another is a third-party dependency. The in-project dependency means the project we depended on is also located inside this repository. So you can access to the source code directly. And to depend on that, thanks for the Gradle Composite Builder, you just need to add the project you depended on into the settings.gradle file, and you can reference it without the specific variant number. So in some cases, the Gradle Composite Build itself is a source of truth for the dependency variance. And another one for the third-party dependency, it means the libraries you depended on whose source code is not located together inside the repository. And in this case, we use the variant cataloger, which is a TOML file, normally sits at the top level of the Monorepo. And inside the TOML file, we specify all the specific third-party variants the projects need depended on. For example, since we are building for the Kotlin, we want to specify the Kotlin variants. And here is a look at the details of that file. We specify the Kotlin variant, and we also specify the Kotlin standard libraries, the modules, which depend on the Kotlin variant. And for each project inside the Monorepo, they can directly reference to the Kotlin-standard lib. So all the specific variant is sit on this file. So the variant catalog TOML file is a source of truth file to specify all the dependency variants. Okay, let's follow up the previous example. And this graph you are looking at is called a reverse dependency graph. This basically, this graph specifies all the relationship of dependencies between each project sitting inside the Monorepo. For example, you can see the library 1 is dependent by library 2. Library 2 is dependent by service 1. And also the service 2 is depends on library 3. So just give you a simple question. What if we make a change of library 3? which project is get affected? Okay, so the answer is library 3, since it's directly affected, and also library 2 and service 2, since they depends on library 3, and finally service 1, because it depends on the library 2. And this 4 project is all the change the project impacted by my change list, and this 4 project is the only projects needed to get reviewed and retest. And the process to calculate to get this list of change projects is called affected targets computation. And by doing this, we can skip a lot of untouched projects and save a lot of building time. And also, again, thanks to the Gradle Composite Builder, we can calculate the reverse dependency graph very quickly, because we specify everything in the settings.gradle file. And also, you should keep remember the variant catalog TOML file mentioned before. We also take that in consideration as well. So if you make change all the specific variants inside the TOML file, it will also treat it as the project dependent is gets changed. All right. The next is distributed builds. So we have the list of change projects. Now we want to build it. And this is the in-house service we created based on the factor each project can be built and tested independently in the Gradle Composite Builder. So this is the overview of the pipeline. On the front, we have the web portal receives the build request, and inside of the build request, it specifies the repository name, git commit SHA, and of course the list of changed projects. Then it's put into the event queue, get picked up by the controller, which is kick off the actual distributed building process. So the controller will, based on each build task type, and put to the corresponding task queue. For example, if this project needed to build in AMD architecture, then it's put into the AMD task queue. And if another project needed to build on the ARM architecture, then put into the ARM task queue. And behind each task queue is a bunch of work nodes with a specific environment to actually run the Gradle building processes. And this good thing is this build service is very extensible. So you can add more task queues behind the controller. For example, we can not only build for the Kotlin, we can also build for Go, build for web, and so on. And the build work nodes do not directly talk to each other. However, they will share the remote build cache with remote build cache, which is also a great Gradle feature. Yeah, let's take a little bit deeper into the work containers. We have 2 types. One is ephemeral. This means when a build request comes in, we boot up containers to do the building. This is used by most of the CI systems, such as Jenkins. And this is also where our journeys began. So in the ephemeral tester, it gets the building and till done after the build is finished. It is good for the limited resource used. So if there is no build request, there is no resource get provisioned. And but it requires some boot up time, right? And the boot up time may be non-travel. So it could count for the up to 50% of the entire CI time just needed to put up new containers. And also it do not support the local parallelization because the container will chill down. So we change to the long-running container, which means the container never gets chilled down. There is a 0 boot up time, and we can also isolate the Gradle daemons inside each container to make it a local parallel building. And another good thing is since the container is not chilled down, the local build cache will sustain. So we can take advantage of the local build cache as well as the remote build cache. Since we changed to the long-running container, it saves us up to like 80% of the overall CI time. Yeah, this is all the some technical I want to share about, and I hand over to Ashwin for the takeaway.
Thank you, Yunji. So let's talk about the benefits that we've seen from this. Right. So The biggest improvement was because like the projects retain their independence due to composite builds. We have a great IDE experience that we can provide to our developers. Because of distributed builds, cross-cutting changes can run a full CI suite in a very reasonable amount of time. We have been able to propagate a significant reduction in service boilerplate code, which makes it easy to also propagate best practices, reduces the amount of code that can generate technical debt. And because it's so easy to generate new libraries and services using code generator tools, we've seen a significant increase in code sharing and reuse. I also want to talk about what we're thinking about next. So we want to explore the remote parallel execution model for other parts of the stack and other build systems. We feel like it's something that could be pretty beneficial, as Yunji mentioned, for Golang, for example. And we also want to continue onboarding more projects to our Monorepo and addressing any other scaling challenges that come up as a result of that. Naturally, a project of this proportion would not have been possible without the involvement of several teams. I would especially like to thank all the people who are mentioned here. And that's all. Thank you so much for coming. We're here to answer any questions that you might have. I think we have time for a couple of questions, and we'll be in the hall outside for any others.